In practice, what does that mean? Okay, in models there is a problem called multicollinearity. Okay, multicollinearity is a problem when you have y is a function of f x1, x2, x3, xp. Okay, you have p number of variables. Okay, now you are working on a problem like the Bezosity score, so anything that comes into your mind you include as a variable just because data is available. So then you have say 25 variables, okay, or 30 variables or 50 variables. Okay, I have seen people doing or working on problems with large number of variables. Okay, and it's not very uncommon in machine learning or data science sort of context where the context is different. We will talk about it later, and explanatory versus predictive problems. But from a statistical standpoint, multicollinearity is not a desirable condition. What does multicollinearity means? Okay, if you have p variables, there are variables which are strongly correlated to each other. For example, x2 and x3 are strongly correlated. Suppose x2 is date of birth and x3 x2 stands for date of birth, x3 stands for age. Okay, of course date of birth needs to be coded, but it can be a sort of ordinal data. Now you look at this, these two variables are included in a model. As soon as you see this you feel, well, this doesn't look good. Okay, why it doesn't look good? Because one contains the other, okay, or they are strongly correlated. They are strongly correlated to each other. Okay, there is a strong correlation between them. Okay, or in other words, the information that is there in age is already there in date of birth. You don't have to include both age and date of birth in a model to depict how old is a individual. Okay, and so what is the reason why you should not do it? Because one particular aspect of an object, okay, is overrepresented. Okay, suppose other aspects that you are trying to include is, say for example, income, or it could be education. So you are actually building the profile of a individual. Okay, or it could be region. Okay, you have included different demographic variables to profile a customer, and then you have date of birth and age. Okay, both talk about the same thing. So what happens is, when you build a model like a multiple regression model, each of this will get a coefficient. Okay, each of this will get a coefficient, and what happens, because one dimension is overrepresented, it affects the representation of other variables, or in other words, the age of the individual gets overrepresented in the model, which leads to underrepresentation of other models, which is not desirable when you are building a explanatory model. Okay, explanatory model. We will talk about it a little more as we go, why we call or we highlight this problem in the context of explanatory models. Okay, so how do we address multicollinearity? So essentially the idea is, if two variables are strongly correlated, have only one of them. Okay, you can do away with age, have date of birth alone, or do away with date of birth, have age alone, drop one variable. Okay, that is the principle. Now how do you do that? You can actually set up a correlation matrix, a diagonal matrix. Okay, and you have x1, x2, x3 here, x1, x2, x3, xp here. Okay, and then you have all the correlations coming here, right? So you can see which are the pairs of variables which are strongly correlated and drop one of them if they are strongly correlated. Set a criteria. For example, if Pearson coefficient of correlation is greater than 0.6 or 0.7, drop one of them, or 0.5. Okay, that's a judgment. Okay, this is one way of addressing the problem, look at the correlation coefficient, but that doesn't address the problem completely, okay, because it is only looking at pairs. It is also possible that the information is in x1 is contained in x2, x3, x4, xp. Okay. In that case, what do you do? The correlations doesn't help because it's only looking at pairs. Okay. So then you need to model x1, or you need to model each independent variable, independent variables meaning x1 to xp, in terms of rest of the independent variables, and have some measure of how x1 explains rest of the variables, okay, and that explanatory power of one variable through other variables is available in a measure called R square, called coefficient of determination. Okay, I will explain this a bit later when I try to demonstrate you how a simple regression model works in order to build understanding about explanatory and predictive models. Okay, but in this at this point, just be informed that R squared, like the correlation coefficient, is a measure of the explanatory power of a model, or explanation of a outcome variable in terms of rest of the variables. So therefore, R square is something that varies from 0 to 100. Okay, 100 meaning the x1 is fully explained by x2 to xp, 0 meaning there is no correlation between x1 and rest of the variables. Okay, so you can actually again use R square as a basis for determining whether a variable should be included or not. Okay, there is a specific measure called variance inflation factor, or VIF, which is, okay, 1 by 1 minus R square. 1 by 1 minus R squared. Okay, and generally if VIF is greater than 2, okay, if VIF is greater than 2, then delete that variable. Delete which variable? It is x1's VIF that is determined. Okay, the idea being, or the principle being, the information in x1 is already contained in x2 to xp because there is a high R square. Okay, so x1 is explained by x2 to xp, in other words, and therefore you don't need x1 when x2 to xp are there. Okay, so that is another way of addressing multicollinearity. So you saw there is correlation matrix, that is step 1, and then VIF as the basis for including or excluding variables in a model. Okay, so this is the third principle, as we have seen in deciding on variables. We have seen 4 principles. We include if a variable is relevant, if a variable is useful in controlling or explaining the outcome. Third is, well, do that but don't have too many. And fourth is, see and ensure that data is available for the variable that you include. Okay. In some literature, this is also called autocorrelation. Okay, especially in econometrics. Okay, now we move on to the next step. Okay, so we looked at step 1 and step 2 in the analytics process, and what is step 3? Okay, collect data and formulate model. Well, we are okay now, right? We have thought about what we are going to do. We have decided our variables. We have ensured that variables are the right variables, and data is available for the variables that we have selected to build the model. Now, what is stopping you now? So, go ahead and collect data, okay, and get the data and formulate the model. Okay, formulate the model. Okay, it doesn't even say fit the model, formulation, okay, or specify the model, and also of course subsequently you have to see how the model works. Okay, that is the step 4. So collect data and formulate model is the next important step in the process of analytics. Okay, so let me actually elaborate to you what does that step really mean. Okay, here is an example of data collection and using data for model building. Here is an example of data that is collected and ready to be used for model building. Okay, and this data I am charting here as an example of how you need to look at data before you use it for modeling. Okay, so this data corresponds to a fashion retailer in northern India, specifically in Faridabad, and the retailer has shared with us data for pilot data for a few years, which pertains to sales, okay, of a particular store. As I said, it is store sales. Okay, not only sales but also discount. Discount is in red, and this is sales. Okay, this is discount. Okay, okay, and you can see that this is for the year 2008, and this starts with January and ends in December. So it's for the full year month wise aggregated data. Okay, monthly aggregated data over 1 year. Okay, and you can see the different charts. The two charts have different scales. So the scale of sales is in the left axis, sale of discount is in the right axis. Okay, and discount is in percentage and sales is in absolute units or in Indian rupees. Now with this plot, if you look closely at this plot, what do you think? So this is something I show students for them to think and respond, and oftentimes they look at the data for some time, and the typical responses I get, which you also may be thinking now, is, well, sales and discount seem to be correlated sometimes, okay, and sometimes there is no correlation. They are trying to increase discount here, but still sales is decreasing. Okay, and oh, this is fashion retail, should they be increasing discount so much? Well, in fashion, if you have discounted sales, you know the affluent class of customers may not even go or look at that, because they don't want such kind of products as fashion. Okay, so all this sort of business knowledge will come when they look at this data. And also someone would towards the end look at the year. Sir, this is 2008, and that is a year there was a financial meltdown. Okay, so there you had a global financial crisis during the year 2008. Okay, that explains. Okay, you get into explanation. That explains why they are giving discount and sales is not coming up, and so on and so forth. And all this information is not, unfortunately, there in this chart. Okay, you are getting into a lot of hypothetical situations. Okay, what is there in the chart? What is there for an analytical mind or an analyst who is going to use data to model, interpret and apply should pay attention to here? Okay, that is something oftentimes people rarely pay attention, but some people do. They notice, well, sales touched 0 here, but discount is still on. Sales touched 0 in the month of March, but of course it was declining, and of course after the month of March it is also going up. But we know that it is monthly aggregate, so therefore for some period of time which covers a whole month, the store sales is 0. There was no sales in the store. As soon as this is highlighted, immediately the answers are, well, there was a strike, there was labor problem, there was short supply, there was financial crisis. You start giving a lot of reasons. as to why there was no sales. It was all your conjectures or all your imaginations. Okay, these are not real reasons. Actually, if you ask, is this a problem? Yes, this is a problem. This should be a problem an analyst should actually spot when you look at data. Okay, and what is this problem? There is no sales. And instead of you deciding as a analyst whether the counter was down or there was some problem, etc., etc., you better ask. If in doubt, ask, don't assume. If in doubt, ask, don't assume. So, since this was a pilot project we did, we contacted the CIO and showed to the CIO, you don't have any sales in the month of March, is that true? He said it is not true. Then what happened? Then he looked at the database and said, well, we had a problem with data collection during that period. What happens is that at the end of the day, okay, the POS, okay, the point of sale systems, transfer data to the data center, as a batch process every day at the end of the day. So it doesn't transfer real time, the data is transferred at the end of the day. And for 1 month there was a problem, there was a technical snag because of which data was not transferred to the database. Now what do you say? Was it a business problem, okay, that there was no sales, so that you should include that in the model? The general principle is that all patterns in the data should be captured to build a model. Okay, otherwise you are not properly informing or training a model, etc. Right? We will talk about it later. But here, this is not something that actually happened to business, but this is a technical issue. Okay, therefore, the title of the slide is inspect data. Okay, or this is in data analysis we call it missing data problem. Okay, there is actually missing data in the data that you are going to analyze. There was the actual phenomenon was happening, okay, which is about sales, but we don't have data about it. Now we have a situation when if you simply say it is 0, it is not correct. The model you could build, but this model is not useful, or the model is not learning properly because you don't have the right data. So in real life, before you go on to build models, when you collect data, there is a problem called data quality. Data quality is an issue in analytics or data analytics, and I will underline this because this is a important factor. The quality of the data determines quality of model. Okay, if you build a model using garbage is the output. Okay, we all know that, and therefore it is important to spend enough time on data preparation. Okay, and that is when you look at data and its characteristics and look at data quality as an aspect of data. Okay, and your textbook talks about 6 attributes, okay, or 6 characteristics of data quality, okay, which includes accuracy of data, whether the data is captured accurately or not, okay, then completeness of data, that is where the problem of missing data comes. You have a lot of missing data, and therefore that is something that needs to be addressed before you use the data. And consistency. Okay, what is consistency? Consistency is, there are different aspects to consistency. One aspect is the units of measurement should be in the same units. Data should be measured in the same units in all the records. For example, suppose you are working on a customer loyalty program and you are trying to segment customers based on customer value, customer recency, frequency, etc. But your customers are dispersed throughout the globe. in different regions of the globe. Suppose you want to build a model that covers the whole globe, that may not be the case often, but suppose it covers multiple countries, then your data is collected from multiple countries. So in some countries it may be dollars, some could be Indian rupees, in some places it may be rupees but a different rupee. Okay, so there are different currency units that are used in different countries, and there is a need to standardize it, otherwise all these measures mean different. Okay, it is not consistent data. Okay, so in this slide there is an illustration of a problem which happened in 1999 because of the confusion of unit of measurement. This is a classical problem often used in data analytics. That is one of the NASA projects. A climatic orbiter actually crashed after reaching close to the Mars orbit, and the reason after investigation was that there was a confusion in the units of measurement in distance measure. Okay, for example, distance was measured using feet and meter, and the data got mixed up, in raw terms, some kind of a problem which has to do with consistency. Okay, and timeliness. Okay, data should be collected using certain timeline. Okay, this is something I am going to explain later. Okay, what does timeliness means? Okay, there is something called cross sectional data. Okay, there is also time series data. In time series data should be collected at regular intervals. That regularity is important. There should be a constant frequency, and if it is not followed, the data is not useful. In cross sectional data should be collected at the same time from multiple points, and if you don't collect data at the same time, then it is not useful. Okay, so depending on the nature of model and nature of problem, one should pay attention to timeliness. Okay, and should check or inspect data to ensure what is the time at which the data was collected. Okay, so therefore the key point I am trying to stress here is, when you are shared with data and the data has lot of column, okay, columns, each column has a title, okay, A, B, C, D, okay, and you see a lot of data. Instead of looking at the data, first look at what are the column titles, what do they talk about, do you understand what it means? Oftentimes the ABCDs will be coded titles, okay, and you don't understand what is the meaning of that variable itself. Okay, always ask for metadata or description or data dictionary, etc., which accompany databases, where a proper description of each column is available. Ask for that column data or column metadata details. Okay, don't accept a data set if it is coded and you don't understand what that code ABCD mean. Okay, get the descriptors and then look at the data and ensure that data is in the same unit, data is timely. Also ask what time the data was collected. Okay, have that specific information that defines the context of the data, instead of simply accepting the data that is given. If you are working on a cross sectional model, ensure that data is collected at the same time. Okay, you have to ask that question, only then you will know. If you don't ask question and assume that it is cross sectional data and it is not, you are actually doing a disservice to organization in building very very misleading models, okay, which can misinform decision makers. Okay, the other aspect is believability of the model, okay, or the data. Okay, when you look at data itself, sometimes you may develop doubt whether it is correct or not. For example, in the last slide we saw that there is no sales in 1 month. Can you believe it? Was the store closed for 1 month? Generally not. Okay, so there is some problem to believe this data. So you have doubt, you start asking questions. Okay, so believability may arise out of several aspects of the data. Okay, when you look at the data, look at the hygiene. Are they in the same units? Are they collected at the same time? Or if it's a time series data, is there a regularity in it? Okay, and where was the data collected? where was it stored, etc., etc. Okay, ask a lot of questions about data before you start using the data. Okay, and interpretability. Interpretability is another aspect of data. Okay, for example, somebody is talking about age. Okay, age is one of the variables. Okay, and some data the age is 2000. Okay, do you believe that somebody's age can be 2000? Okay, so this is common sense, but it is not interpretable. There is some issue. You immediately make out that there is some problem here. Okay. Okay, we saw that database will enforce certain rules when you actually input, say, a timestamp, etc. But that actually takes care of this problem. So many of this data quality concern can be addressed through tools which are available for so-called anomaly detection. Okay, anomaly detection. Anomalies in the data can be detected automatically today through tools. There are tools available, but what goes into these tools is concerns and questions like this what we are dealing with. Before I move to the next slide, let me also talk about another trivial but potential problem when we look at data. Okay, this is a question I ask students. If you okay, if somebody writes, how much money is this? Okay, of course this is in euros. You can easily interpret the euro sign. How much money is this? So as Indians typically we will respond that this is 1 euro. But ask a German, how much money is this? Okay, and they will immediately make out this is 1000 euros. Okay, this is 1000 euros. The dot, okay, has a different meaning as a decimal separator in different countries, in different regions, and one must be aware of it. The comma separator is used in many countries like India, Britain, Americas and so on, but comma separator is not used in certain European countries. It is a dot that is used instead of comma, and if you are not aware of it, again your interpretation of results will be misleading. So data, okay, data is the basis. Let's move on to the next lesson. So we discussed data problems in the real world, and I try to summarize that in the previous slide, and I try to highlight the problem as a big problem. Okay, data quality is very important in analytics. Okay, in class exercises it may not be important because you are only learning how to use algorithms, but in analytics you are applying algorithms for real life problems. Okay, missing data. Okay, there are techniques for addressing missing data. One is missing data substitution, depending on the extent to which data is missing. Okay, so you can substitute with the average of the neighbors or average of the row, etc. There are different techniques that are recommended in textbooks, okay, on data preparation for data mining. Okay, and noise, you can use filters. Okay, you can use different techniques to address outliers. Okay, you must have learned those methods in data analysis, basic data analysis, which is a prerequisite for this course, and we have talked about inconsistency and other issues already. Okay, so let me move on. Okay, so data pre-processing is a very important step for data mining and analytics. Okay, and this becomes critically important because oftentimes the analyst does not have any control in the production of the data. Data production is done somewhere. Okay, you are actually accessing secondary data, that is data which is already captured and stored based on certain design of the database and data warehouse or some other source, and you are granted this data. You did not design an instrument to collect this data as you do in survey or experiments, where the instrument is designed by the researcher, and therefore you have complete control on the range of data, on the scale of data, and what the different variables together constitute or construct, etc. Okay, there you have a lot more control on the quality of data. Whereas here you don't have, because there is large volumes of data collected by someone, stored somewhere. You need to actually work on that to make it useful, okay? And therefore you apply techniques like this. Most of this we have already discussed, okay? There is also data transformation that is required often. We are going to discuss that in another slide.